watt var impedance calculation from voltage current waveform. Actually, electric power supplier face the problem to supply the power to electric power consumer and tariff rating and rating. So the first consumer was earlier days. First consumer was lighting, then afterwards heater, then motor was invented. Motor consumption was in lagging power factor, lagging load was happened. So they decided watt and var component. Watt is for tariff calculation. Var is exporting to the system and importing from the system. So var is not calculated for tariff purpose. Watt only is used for tariff purposes. Now we analyze one by one. Here we are seeing two waveforms. We are going to analyze these two waveforms. Block is voltage waveform, it is current waveform. In this waveform, peak to peak value, voltage peak to peak value, and V maximum value. Maximum value is maximum in the positive half cycle of the waveform, that is equal to VPP by 2. IPP, I maximum, or current peak to peak maximum value of current waveform. VRMS equal to VPP peak to peak whole divided by 2 into root 2, that is equal to V maximum divided by root 2. Similarly, IRMS equal to I peak to peak divided by 2 into root 2, that is equal to I maximum divided by root 2. Example, if voltage peak to peak is 282 volt or V maximum is equal to 142 volt. I peak to peak is 1.414 volt or I maximum is equal to 0.707 ampere. VRMS equal to 282 volt divided by 2 into root 2 or 142 divided by root 2, that is equal to 100 volt. That is VRMS equal to 100 volt. IRMS equal to 1.414 divided by 2 root 2, that is equal to 0.707 by root 2, that is equal to 0.5 ampere. IRMS equal to 0.5 ampere. From waveform, period T is equal to 20 millisecond. That is frequency is equal to 1 by T, that is equal to 50 Hz. One cycle equal to 360 degree or 20 milliseconds. 360 degree equal to 20 milliseconds or 20 milliseconds equal to 360 degree. If you want to convert to other timing, 10 milliseconds equal to 180 degrees. That is 360 into 10 divided by 20 is equal to 180 degree. Suppose the time is 5 millisecond, 90 degrees, that is equal to 360 into 5 divided by 20 is equal to 90 degree. 1.66 milliseconds corresponds to 30 degrees. Now we are going to see phase angle. Here two waveforms shown, one is voltage waveform, one is current waveform. Phase angle, voltage waveform is considered as a reference waveform and rising edge of the waveform's zero crossing point are considered as a reference point. Duration between current waveform zero crossing point and voltage waveform zero crossing point is called lagging time. Lagging time is converted to angle, that is lagging angle. If measured time equal to 10 millisecond, then 180 degree is lagging with reference to voltage. That is current is lagging by 180 degree with reference to voltage. Suppose if the angle is measured time is 1.66 millisecond, that is equal to 30 degree. Current lags with reference to voltage by 30 degree. If measured time is 11.66 milliseconds, that is equal to 210 degrees, current lags with reference to voltage by 210 degrees. If suppose the measured time is 8.33 millisecond equal to 150 degrees, current lags with reference to voltage by 150 degree. 18.33 millisecond corresponds to 200 degrees. Current lags with reference to voltage by 200 degrees. These waveforms are represented as vectors as given below. RMS values are magnitude and delayed time are lagging phase angles. Generally, V is considered as reference waveform and voltage vector as reference vector with phase angle equal to 0 degree. You see here, we consider single phase voltage and current waveforms only. Now VR and voltage and IR waveforms are considered. Two waveforms here, that is VR voltage and IR current waveforms are shown here. The same is applicable for three phase also. If you are going to see for three phase, same is applicable. In vector calculation, clockwise is called lagging minus angle and anti-clockwise is called leading plus angle. Now you see here two figures are there. Figure 1 is lagging by 30 degree theta, that you can represent it by I angle minus theta. In figure 2, I leading by 30 theta. I leading by theta means I angle theta. Lagging angle can be represented as leading also. Minus angle theta is equal to 360 minus theta angle. Angle theta is equal to minus 360 plus theta. First case is lagging, second case is leading. Lagging angle can be represented as a leading angle. Leading angle can be represented as a lagging angle. Now here you are seeing the wave connection of the measurer or relay. This is one side is bus is connected to the feeder. Power flow from P1 to P2, that is current flow from P1 to P2 in the primary system. Secondary system S1 to S2, that is connection diagram of measurer or relay. 7 and 8 are voltage terminals and 9 and 10 are current terminals of measurer or relay. When current flows from P1 to P2, secondary current enters in 9 and current comes out from 10 of measurer or relay. Most of the meters shows phase angle without sign, that is a plus or minus. Angle shown in the meter is current lagging angle with reference to voltage. For watt/var impedance calculation, sign is important. We are going to analyze four types of load current. Here you are seeing four types. One is inductive load in the forward direction, capacitive load in the forward direction. Another case is inductive load is in the back side of the measurer unit, or capacitor is back side of the measurer unit. We will see one by one. Case 1. Here source is connected to back side of the relay or measurer. Load is connected to forward connections. If you see in the vector connections, current is lagging with reference to V by theta. Here the angle is not shown here, minus or plus, it is lagging angle. Now case 2, capacitor load. Source is feeding the capacitor. The measurer is seeing the load. In vector connections, vector representation, I is leading with reference to voltage, or I is lagging with reference to V by theta. Now case 3. It is reversal of the earlier case. Load is connected to the back side of the measurer and the generator is connected to the front side of the measurer. Here, if we see the angle and the voltage vector, I is lagging by theta degree. Another case is capacitor load, capacitor load. Here, capacitor load is connected to the back side of the measurer or relay. Source is connected to the front side. Here this vector diagram, I is lagging by 30 theta. Now if we see all combined together, first case is inductive load, front in the feeder front side, generator is the back side. Second case is capacitor load is the front side and generator is back side. Case 3, it is reversal of case 1. That is, inductive load is back side of the measurer unit and generator is the front side of the measurer unit. Case 4, it is a reversal of case 2. Capacitor is in the back side, the source is in the front side. In that case, how it is behaving and like that we will see that one. Now, we measure the voltage and current of each cases. Case 1, voltage as I told you, voltage we take as a reference. In all the cases, 100 volt angle 0 is a voltage. Current, in first case, current is 0.5 ampere with the angle minus 30 degree. Second case, 0.5 ampere minus 330 degree. Third case, 0.5 angle minus 210 ampere. Case 4, 0.5 angle minus 150 ampere. Here CT ratio, PT ratio is 1:1. So whatever the primary current, primary voltage that will be appearing into the measurer unit or relay. Now, first we will see, we got that two quantities, voltage and current. This is measured quantity. Now we are going to see the derived quantity, watt and var. Before that one, we have to see the conjugate of current. Conjugate, conjugate of the value means it is a reversal of the conjugate. First case, conjugate of minus 30 degree is plus 30 degree. Second case, minus 330 means 330. Third case, minus 210 conjugate is 210. Fourth case, minus 150 conjugate is 150. Now I conjugate we got it. Now VI conjugate. Multiply both the things, voltage and I conjugate. First case 50 angle 30 VA. Second case is 50 330 VA. Third case is 50 angle 210 VA. Fourth case is 50 angle 150 VA. Now if we convert this to polar coordinations, VA conjugate is equal to P plus JQ. First case is 43.J25. Second case is 43.3 minus J25. Third case is minus 43.3 minus J25. Fourth case is minus 43.3 plus J25. That is, first real is called watt, imaginary part is called var. First case is in the first coordination. Second case is in the second. In the first case, you see that one, watt is positive, var is positive. So, it will fall into the first quadrant. In the second case, watt is positive, var is negative. Second case, fall into the fourth quadrant. Third case, var is negative, var is negative. It will fall into third quadrant. Case 4, watt is negative, var is positive. That is, it will fall into second quadrant. You see the current waveform, vector waveform and this watt and vectors. Here, conjugate of that value only you will get it. What about power factor? First case, power factor is nothing but cos theta. First case, it is lagging. So, cos 30 is equal to 0.866 lagging. Second case is leading, 0.866. Third case is minus 0.866 lag reversal. Fourth case is minus 0.866 lead reversal. Now you see combinedly watt var plane and impedance plane. impedance plane is not important now, but even though you can compare that one, V by I is equal to impedance. See, first case is current is lagging by theta, that is inductive load. In the first power plane, VA fall into first quadrant. Same way in impedance plane also, it will fall into first quadrant. Second case is capacity load, that is first case current the watt/var plane, VA fall into fourth quadrant. Same way RX plane also, Z is fall into the fourth quadrant. Case 3, reversal of the first case, that is VA fall into third quadrant. Same way Z impedance also fall into the third quadrant. In case 4, reversal of the inductive load, capacity load, that is VA fall into second quadrant, immediately impedance fall into second quadrant. Till now we have seen the secondary power only. If you want to convert into the primary power is equal to secondary power into CT ratio into PT ratio. Suppose the secondary power case for case 1, primary CT ratio is equal to 500 bar 1 and PT ratio is equal to 110 kV bar 110 volt. Then primary power is equal to 50 angle 30 into 500 into 110,000 divided by 1 into 110 equal to 25 angle 30 MVA. For 3-phase, primary power equal to summation of 3-phase power or 3 into single power. In the same way, we can calculate the other phases also. So, from the waveform, you can calculate watt and var of the load. That is, if it is the forward direction or reverse direction. The relay will not see the lagging or leading. It will compare the angle. It will see the angle 0 to 180, 360 degree in the reverse minus lagging angle. Primary impedance equal to secondary impedance into PTR divided by CTR. Secondary impedance for case 1 is equal to 200 angle 30 ohms. If CTR is equal to 500 bar 1 and PTR is equal to 110 kV bar 110 volt, then primary impedance is equal to 200 angle 30 into 110 0 into 1 divided by 110 into 500 equal to 400 angle 30 ohms. That is equal to 346.4 plus J200. For 3-phase balanced load condition, no neutral current or no zero sequence current. Primary impedance for single phase is same for phase to neutral and phase to phase. That is impedance for Rn, Yn, Bn, Ry, Yb, Br are same. With 3-phase balanced load condition, single phase primary impedance is equal to 400 angle 30 ohms. Primary impedance for Rn is equal to 400 angle 30 ohms. Primary impedance for Yn equal to 400 angle 30 ohms. Primary impedance for Bn is equal to 400 angle 30 ohms. Primary impedance for Ry equal to 400 angle 30 ohms. Primary impedance for Yb equal to 400 angle 30 ohms. Primary impedance for Br is equal to 400 angle 30 ohms. Conversion of power to impedance. It is not required, but even though this is included in this portion. For case 1, secondary power is equal to 50 angle 30 is equal to 43.3 plus J25. Applied voltage V is equal to 100 volt. R equal to V squared into watt divided by watt square plus var square. X equal to V squared into var divided by watt square plus var square. Sin R as in watt var. R is equal to 100 square into 43.3 divided by 43.3 square plus 25 square equal to 173.3. X is equal to 100 square into 25 whole divided by 43.3 square plus 25 square equal to 100. Watt sin equal to plus, var sin is equal to plus. So R sin is equal to plus and X sin is equal to plus. So Z is equal to 173.3 plus J100 equal to 200 angle 30. That is Z is equal to 100 divided by 0.5 angle minus 30 is equal to 200 angle 30. If CTR is equal to 500 bar 1, PTR is equal to 110 kV bar 110, then primary impedance, secondary impedance into PTR by CTR is equal to 200 angle 30 into 110,000 into 1 divided by 110 into 500 is equal to 400 angle 30 ohms. For case 2, watt sin equal to plus and var sin is equal to minus. So R sin is equal to plus, X sin equal to minus. Secondary impedance Z is equal to 173.3 minus J100, that is equal to 200 angle 330 ohms. Primary impedance equal to 200 angle 330 into PTR by CTR equal to 400 angle 330 ohms. For case 3, watt sin is equal to minus and var sin equal to minus. So R sin is equal to minus, X sin is equal to minus. Secondary impedance equal to Z is equal to minus 173.3 minus 100 is equal to 200 angle 210. Primary impedance equal to Z is equal to 200 angle 210 into PTR by CTR equal to 400 angle 210 ohms. For case 4, watt sin is equal to minus, var sin is equal to plus, so R sin is equal to minus, X sin is equal to plus. Secondary impedance equal to Z is equal to minus 173.3 plus J100, that is equal to 200 angle 150 ohms. Primary impedance Z is equal to 200 angle 150 into PTR by CTR equal to 400 angle 150 ohms. Thank you very much for watching the video.